Okay, are you recording? Cool. All right. Hi, everyone. Welcome to Sustainable Engineering Workshop. My name is Addie, and I'm really excited to teach this because this is something that I've been interested in for a while. My background pre-college was actually in environmental science and biology and ecology and a little bit of earth science. So this is kind of more my field than engineering really is. I'm also a data studies minor, so I've done a lot with the topic outside of engineering. I think the university does not do a very good job of teaching it. So I'm excited to get this opportunity too. First of all, introduction. What is sustainable engineering? I don't think. Can you me now? Hang on. Okay. I don't know what's going on. I don't know if they can see me on Zoom. Hang on. There we go. Okay. Now people can see me. Thanks. All right. Let me try that again. Sorry, guys. Okay. So first of all, what is sustainable engineering? Sustainable engineering is engineering that takes the well-being of the environment and its organisms, including but not limited to humans, into account, and it accounts for its effects in the short and the long term. So that focuses on energy efficiency, carbon emissions, resource acquisition and use, where your stuff is coming from, the waste you produce, and environmental protections as well. This is kind of a diagram that's showed a lot in regenerative studies, where you kind of see, it's a visual representation of kind of where we are right now and where we need to be. So you can kind of see on the screen, you've got, your conventional systems, your sustainable is right in the middle. That's kind of, not doing any harm, but not doing anything great as well. And then regeneration, which is kind of like working to actively fix things. That's kind of what this workout should be called, but for branding purposes, I decided sustainability was probably a term people recognize more. But this is just kind of an overview of where we are and where we need to go. Why are carbon emissions bad? Hope we all know this, but it exacerbates the greenhouse effect, which is the effect that keeps our planet warm. So it retains heat from the sun. And normally that's great, but we have exacerbated that to the point that it's becoming problematic. So you can see on this chart right here, normally, historically, it's been 300, maybe 300 is about where it's been. That's like the highest point, and it's gone up and down. And then you hit humans. That's the industrial evolution. And we're at like 420 right now. So it's way past what it has been in the past at any point. And this is really bad for a variety of reasons, increasing frequency and intensity of extreme weather events, including but not limited to droughts, floods, heat waves, wildfires and storms, human health impacts, including heat stress and increased transmission of some diseases. Increased heat conditions create conditions for some disease vectors like ticks for Lyme disease or mosquitoes for malaria. So you can see those increase as the temperature warms. Ocean acidification, coral bleaching, rising sea levels, biodiversity loss, and human conflict as resources become iffy. It's possible people fight more. So this is kind of a problem. If you want to know more about how any of these things affect us or how climate change causes them, I'm happy to answer your questions, but I do want to move on right now. So talk to you later. And then there's other environmental issues not exclusively related to climate change, including pollution of air, water, and soil, deforestation and desertification, habitat destruction, biodiversity loss, and just the epic amount of waste we produce. So that's kind of what happens and why we need to change our practices. Why should you care? I could totally talk about this from a perspective of, animal rights or whatever, but it also affects us in a lot of ways that we forget about because we're so detached from it. That includes air and water filtration, pest control, pollination, soil management, food and resource protection, carbon sequestration, and oxygen production. So all of these things are roles that the biosphere fulfills that we kind of need to live. So that's why this is important. And then there's also the regulations aspect of it. So you've got AB 1279, that's the California Climate Crisis Act. And it establishes that California wants to achieve climate neutrality no later than 2045. SB 1020, the Clean Energy Jobs and Affordability Act. California is aiming to be 100% renewable energy by 2045 as well. SB 905, that requires the California Air Resources Board to establish a carbon capture, removal, utilization, and storage program by, you cannot see this because of the window, by 2025. No, that's okay. And then there's also the 2030 challenge. That was a challenge proposed by an architect quite a few years ago. Basically says that we are going to be carbon neutral by 2030. All of our buildings are going to be net zero by 2030. And over 1,200 architecture firms, I believe, have adapted that, as well as the state of California for their building codes. California is also banning the sale of new gas-powered vehicles by 2035, and a lot of other car companies have followed suit, so they're banning new gas-powered vehicles as well. And then there's the aspect of California's economy. Because California's economy is so freaking big, their regulations kind of affect the rest of the US, if not the rest of the world. So for example, if California is putting restrictions on car emissions in California, which they did, that's an issue for other companies, because if they want to sell in California, they have to meet those requirements. So even if you end up working in a different state, you actually might still have to abide by California regulations. There's also the EU carbon border tax that just passed. That is a tax on certain imports to EU based on carbon emissions, emphasizing products like iron, steel, aluminum, cement, and fertilizers, and so on. And so if you're working in manufacturing or product design, and you're trying to import things to the EU, that's going to affect you financially if your carbon emissions are really, really high. There's also the UN Global Plastics Treaty that's kind of going on right now, that's in the works, trying to curb plastic pollution. So you can see it's not really optional. This is going to be relevant to your careers at some point in the future. And you can see all these goals are like not far from now. This is going to be relevant when you get a job and after that. So why you should care? Everyone good on that? Okay. Moving on. I want to talk a little bit about sustainable design principles. The first is you want to utilize your waste products, both materials and energy, and I'll talk about how to do that later. You also want fail-safes, backups, and contingency plans. Let me move this. Because you always want to prevent and respond to disasters. So fail-safes are really important for preventing things from going wrong. I think if you guys heard about that incident in Ohio about the train derailment, that's kind of an instance of where things went wrong. All the oil spills, other instances of where things went wrong. And then you always want backups and contingency plans in case of instances like extreme storms or extreme weather events, earthquakes, crazy stuff like that. If there's ever some sort of disaster, you don't want your entire infrastructure to collapse. Diversity, multiple components should hopefully do the same thing, and that kind of goes back to those backup fail-safe design. That's kind of relates to ecology as well. The most resilient ecosystems are the ones that have the highest biodiversity, and that's because if one species, if something happens to them, there are always other species that can come in and take their place, fulfill their role. And so you never allow anything to get out of control. And it's the same thing when you're talking about engineering, especially with regards to energy mix and renewables. You never want to have just one, because if something goes wrong, you're screwed. So you want a lot of things that do the same thing, if that makes sense. Also efficiency, if you can solve multiple problems with one solution, that's always helpful. Give you an example of this. There was a proposal to cover, I think it was the LA River, with solar panels. So not only is that providing renewable energy, it is also shading the LA River and preventing evaporation. Or was it failure or was it reservoirs? One of the reservoirs makes more sense, but you get my point, right? So multiple problems with one solution. Biological solutions first, if possible. Please, something invasive. Work with a biologist if you can't, if you don't know about this. One is that there are ways to do it that don't involve technological solutions, and that's kind of like the struggle that a lot of engineers have, is they don't realize how to work with solutions that are out of their fields. But it's really important for people to do that because the engineering solution might not be the best one. Use the least energy intensive solutions first. If you can find passive solutions to problems, that's a really important way to, minimize your energy consumption and your costs related to energy consumption. I'll talk about how to do that later. You always want to consider the effect of the technology or the operation on the worlds around you. So that's another one of the problems they have with engineering that they don't teach. Teachers joining. Is that engineers build a lot of stuff, and that obviously affects the world around you. Engineers don't seem to understand how the natural world works, and so that creates a lot of problems. I guarantee you, if engineers understood like natural sciences, we would not have the issues we have today. I'm not mad at engineering. I'm just kind of like, it's a problem we need to fix, which is why I'm talking about it. And related to that, most really sustainable and regenerative technologies cross disciplines. So work with other people outside of your fields because you'll come up with much better solutions than you would have on your own. And I'll show you examples of that later. And I missed one. Plan ahead, like several generations ahead. That's also something that we do wrong a lot, is we don't consider the impact that we are going to have at a time in the distant future. So example of this is like the tragedy of the commons. If you have the tragedy of the commons, you're not familiar with it, is when you have a shared resource and everyone wants to use the resource, but then that kind of results in the resource being overconsumed, and then no one has access to it in the future. And that's something that happens a lot. So it might not be in your best interest right now, but it could be in your best interest in the future. And that's something it's a really tricky trade-off. It's something that isn't considered nearly enough and should be considered. So I want to talk a little bit about product design, if that's something that anyone's interested in. Plan for the entire lifespan of the product, because products have lifespans. I don't want to say they're born, but they created and then they die, and they don't really go away. They just go out of our sight. And so planning for what happens to them after they're broken is really important. Designing high quality products that are built to last. Planned obsolescence, not cool. It pisses your customers off too. No one likes it when your product is designed to break. Rechargeable batteries and standby or automatic turn off features. Those are great for energy efficiency. Designing products to be serviceable or easily disassembled so that they can be fixed. Once again, lasting a long time. And designing for disassembly. So you have parts that can be reused, recycled, and you want to make sure that that's the case, that they are being reused and recycled. That includes minimizing the number of components, minimizing the number of joints and connectors, and considering what those are. So permanent connectors like welding, rivets, glues, those aren't great. If you've got latches, clips, bolts, screws, snap fits, those are much better. And let me move this again so you can see the picture of the snap fit. Nope. Yes, there you go. Okay. Avoid irremovable coatings if possible, because that makes it really difficult to recycle parts. And design for damage-free disassembly, because that makes it hard to use parts as well. So if your part gets damaged, if whatever you're making gets damaged as soon as you try to disassemble it, not great, just in terms of the life cycle of the product, and for what happens to it when it's done. Also good labeling and documentation. So if you have something that you built, you want people to be able to fix it really easily. So good manuals and good labeling on the parts as well. Make sure that they're labeled clearly. It's very easy to identify what comes apart, when and how, just good practice in general. And a lot of these are just like good design in general. Like I'm framing them as like sustainable design, but a lot of these practices are just good practices in general for engineering. Consider materials. So utilize waste materials when possible. Compostable and recyclable materials, really important. Consider the ease of recycling and composting. I'll talk about that later. Avoid combining biodegradable and non-biodegradable materials. Try to avoid high impact and toxic materials. Talk about that later as well. And especially with regard to parts that are designed to fail. So one of the examples that I got from my classes was we're talking about, product design. And the example he gave us was of some, I think it was at Disneyland, it was a ship. And the design was poorly designed. So the boat took off and was still anchored, someone forgot to take the rope off. And instead of the rope breaking first, the rope was strong as hell. So the anchor was the one that broke, and a big chunk of metal flew off and like hit someone. So that's where it's important to determine what part breaks first, because some part is going to break first. So whatever it is, it's used to the safe part. But it should also be a part that is easy to replace. And if you're talking about waste, you don't want it to be something that's going to end up in a landfill. So if it can be made of something that's recyclable or compostable, that's the ideal. Just some cool examples. These are, we talked about waste materials. This is on the bottom here, the pallet pavilion. That was made in Christchurch, New Zealand, I believe, after, I forget what the disaster was. There was some big disaster, and they came up with all these really cool ways of rebuilding. And this was one of them. And these on top, I'm sure everyone's seen shipping container buildings. Another great way of reusing waste materials in a really cool way. Last one, use as little material as possible. This is also just cost effective. Good design should rely on geometry, not increased mass for strength. So like I'm sure you've all seen trusses, that classic building competition where you have to, you have to create the strongest truss that weighs the least. That's kind of where what this principle is. You can also see I've got that picture there of the ribs. You don't want thick walls, you just want better geometry. And then once again, we talked about good fail-safe design. So sensors are really important in that kind of scenario. We want to make sure that you're keeping track of, keeping track of what is going on in your product. Why can't I move this? Okay, looks like we're moving on. I can't get this thing to move.
Oh, yeah.
There we go. Okay. So why are materials important? The first thing is that Earth is a mostly closed system in terms of matter. So we're always receiving energy from the sun. It's an open system of that source in that scenario. But in terms of matter, aside from the occasional asteroid, we really live on a closed system. And so we are occasionally going to run out of materials. And as they get more scarce, it's going to become really important to choose materials that are recyclable or compostable so that we are not in this scenario where we are having increased labor and cost trying to find materials and eventually running out. That sucks. Material sourcing, pollution and environmental damage and destruction and exploitation associated with material sourcing, generally not good. We want to avoid that when possible. Embodied energy or carbon. So every material has what's called embodied carbon or embodied energy. And what that means is that the process that it went through in making it, including manufacturing or extraction, that had carbon emissions associated with it. And that's the embodied carbon. And so that's something that you have to consider when you're choosing materials, if possible. Toxicology. I'm so sick of seeing the everything's carcinogenous. We've all seen was it Prop 65 for California? This material is known to cause cancer, birth defects. Why do we live in this world? It's stupid. We've accepted the fact that everything is toxic. It's dumb. Yeah, if we can change that, we should be changing that. And as engineers, I think that's kind of our job, is we get to build the world we want to live in. So why would we use things that are toxic if we have the choice? And that's kind of my point with this whole presentation, is that if there's a better way to do things, why would we not do it? Then there's disposal, reusable versus recyclable. Do I need to explain what that is? I think everyone knows that. Compostable versus biodegradable. This is one I think I do need to explain. So biodegradable just means that it will break down at some point under some circumstances, but that could be 100 years from now, and they don't want to tell you when. Companies really like to say stuff is biodegradable, but that doesn't actually mean anything, and it could be biodegradable under very specific circumstances. Compostable means we are guaranteeing it will break down under the conditions of a compost pile. So that is generally better. It depends, but I think compostable is usually what you want to go for. And so that's something you have to consider when you're looking at materials. And then your waste management infrastructure. So like plastics, all plastics are labeled with a little thing that says, type 1, type 2, type 3 for recyclability. And we'll talk about this a little bit more later, but it says they're recyclable, but we don't actually have the infrastructure to recycle like several of those types of plastics. So only of those like 7 types, only 3 of them actually get recycled, if at all. So that's something that we want to consider is, do we have the infrastructure to manage waste if we're producing waste?
Question.
Yeah.
Could you elaborate more on embodied energy? What is
Okay, so we'll talk about this a little more later when we cover materials. Is that actually, I think that's actually our next slide. So if you want to hang on. Okay. So steel. I think our next slide, that should be a better example of this, but steel makers produce 7 to 9% of all anthropogenic greenhouse gas emissions. And that just has to do with manufacturing process, the heat produced and the way that the carbon is melted in some cases. And the best way to reduce emissions for steel is to use recycled steel, processed in an electric arc furnace. You don't really need to know what that is, but electric arc furnaces produce less than half as much carbon dioxide as basic oxygen furnaces. Yeah.
Yeah, can you just hold me that should be minimized?
Oh,
Sorry, logistic thing. All right,
cool. Okay, thanks. There's the 2 types of furnaces that are used to recycle steel are electric arc furnaces and basic oxygen furnaces, and electric arc furnaces produce a lot less carbon dioxide. So that's what you want to go for if possible. Also, virgin steel can have an embodied carbon footprint up to 5 times greater than high recycled content steel. So if you can have recycled steel, that's always better. Concrete, this is the one where I think I'll really explain embodied carbon. It's blocked by this bar up top. It's great placement. You can't see it, but what it says is CaCO3 yields CaO plus CO2. And that is basically the process through which calcium carbonates yield calcium oxide and carbon dioxide. That's the process by which Portland cement is made. It's one of the big components of concrete. So you've got Portland cement, sand and gravel, and then water mixed them together. Most widely used construction material in the world. But that process, you can see for every molecule of limestone, which is the key ingredient in Portland cement, you get 1 molecule of carbon dioxide. So it produces a lot of carbon dioxide. About 60% of the emissions from concrete production come from that reaction. The other 40% comes from burning fossil fuels manufacturing. And in total, that's responsible for about 6 to 10% of global human produced carbon dioxide emissions. So it's a big source of emissions. Ways to remedy this are to use less Portland cement, for one thing. So Portland limestone cement is alternative. It has just higher limestone content, so you're not using as much of that calcium oxide. It's not as much, you're not producing much carbon dioxide in the reaction because you're not undergoing that reaction, you're just keeping it as limestone. There's also a material called volcanic ash that can be used. Actually produces stronger concrete, so better results in the long run. And it's a pretty abundant material as well. You can also use waste products instead of gravel for the aggregate. That includes paper, shells, hemp, glass. I was actually in a class at the Lyle Center with an architecture professor who had us making papercrete. So we did this. There's actually a bench up there made of papercrete that you can see if you go up there. Stuff is very interesting. You can also make existing concrete last longer. So you can see this picture right there, the one near the top, that is actually self-healing concrete. I think that's a really cool example of cross-discipline cross-discipline technologies working together. They added a enzyme from human blood called carbonic anhydrase to the concrete. And what that enzyme does in human blood is it transports carbon dioxide. So in concrete, what it does is it takes carbon dioxide from the atmosphere and turns it into a calcium carbonate, which fills in cracks. So that's a great way to make concrete last longer, and also to crush carbon at the same time, which is really cool. And you can reuse waste concrete. So if you've got old concrete that's not being used, you can actually crush that up and use it to make like walls and stuff. If you've seen, I know you've been to the Lyle Center, you've seen, they've got those walls there that are, you'll see them when you go.
Volcano or the red, like little red rocks and the.
No, it's just regular concrete, but it runs around like the perimeter. You'll see it when you go up there. But that's recycled concrete. It can be used to create walls as well as paving stones on the floor.
How long does it take for the self-healing cement to form that extra?
I'm not sure. I think it's pretty quick, within like a couple, maybe couple hours. It's not, it depends on the size of the crack, but it's not too long. Bamboo is a material I think is really cool. You can see really cool stuff you can do with it in terms of architecture. It actually has greater compressive strength than concrete and the same strength to weight ratio as steel when in tension. Really good tensile strength and elasticity. It also grows fast. Most of bamboo can grow as much as 2 feet in a day. So crazy fast growth. Really good in terms of resource replenishment. And 1 hectare of that bamboo can sequester 109 to 289 tons of carbon annually. So you can consider when it's growing is how much carbon is it sequestering in that case. Really cool. And then this I just found today. I've never seen this before, but it's like,
Bamboo keyboard?
yeah, a bamboo keyboard.
Yeah.
I was like, this is so cool. So it's also a great material to use for like product design as well. If you need like a covering for something, like really nice material if possible. Yeah, so yeah. One thing about most of the technologies I'm showing you today is they are expensive because I'm showing you a lot of the stuff that's newer. As they become more common and as manufacturing capabilities increase, I expect the price to go down. So it's not necessarily something you can implement right now, but something to keep an eye on for the future. That's kind of my point today, is that these are things that you just want to keep an eye on. Also, before I move on, also wood is kind of in this vein of organic materials. One thing I didn't mention here is, of course, this breaks down because it's organic. Wood just grows more slowly, so it's still very possible to use. Just have to make sure that it's being taken in a non-damaging manner. Plastics. So I think we've all heard why plastics are bad. I'll go over it again anyways. They're derived from crude oil and natural gas. They turn into microplastics. They're often very toxic. And they don't recycle well. Despite what you've heard, the same piece of plastic can only be recycled 2 to 3 times before its quality degrades to the point at which it can no longer be used. And every time it's recycled, virgin material has to be added to it to upgrade the quality and make it competitive with new plastics. So when they say it's recyclable, like it is, but only for a certain period of time. Plastics number 1, 2, and 5, those are the ones that we really have the capability to recycle. 3, 4, and 7 are much harder. Those are the ones where they say it's recyclable, but they're really not. Easy. So if you have to use recyclable plastics, if you have to use non-coastal plastics, choosing the ones that are recyclable is always better. If choosing the ones that are easier to recycle is always better if possible. Coastal plastics, you cannot see the diagram. So you've got your non-biodegradable, biodegradable, fossil-based, and bio-based plastics, and you can see there's combinations in all 4 of those categories. So just because they're bio-based doesn't mean that they're biodegradable, and just because they're fossil-based doesn't mean that they're non-biodegradable. If that makes sense. It's a little weird. But the big ones right now are PLA, which are derived from starch, often comes from corn or sugarcane, and PBS. PBS has pretty good impact on thermal resistance, good toughness, good ductility, but limited strength. So it's usually blended with PLA for better mechanical properties, like higher stiffness and better processability. You can actually get these. They have like 3D printed filaments now that are made of these blends. So they'll call it like, I think it's like impact resistant PLA or something. Basically it's a blend of the two, and it's like better than PLA, but also better than PBS. I have not tried it. I wanted to, but it did not come in time. Some plastics are backyard compostable. There are ones that are starting to be advertised that way now, but most of them need industrial composting conditions to break down. So a lot of times you'll hear people say that PLA is biodegradable. It is, but only in industrial composting facilities. It will not break down in your backyard.
What is industrial compost?
So glad you asked. Industrial composting means that the it's a different process. It's the same composting process, but there's a lot higher temperatures. They usually grind the material. It's just kind of like a more intense form of composting. So these biodegradable plastics need those intensified conditions to break down. They're not going to break down on their own. Yeah. So just because it says biodegradable, that doesn't mean that it's going to biodegrade if it gets tossed to the side of the road. It won't. It really needs that composting facility. Okay, talked about materials. But I want to talk about passive solar. So this is great for energy efficiency. What it means is that you're using the building. I better move this. I'm sorry. What it means is that you're using the building structure rather than mechanical systems like HVAC systems to heat and cool the buildings. So it saves money and energy, and you can still use an HVAC system, but you won't need one that's as big as you would have needed before. So the mechanical engineering department will usually teach you, let's make a more efficient HVAC system. The RS department will say, well, let's just make the building as efficient as possible before we need an HVAC system. And then we can add a small efficient HVAC system instead of a big efficient HVAC system. And that's a way more efficient way to do this in terms of energy efficiency and in terms of cost. If you're working for, let's say, a architecture firm or a consulting firm that's working for a building, this will make your clients very happy. It will save them a lot of money, a lot of electricity. Generally, it's good practice. And you can see one of the examples here is that you've got the angle of the roof, so that this angle that the sun is oriented in winter and the angle that it's oriented in summer. It's blocked during summer to allow for cooling, so you're not having as much solar heat gain. But in winter, it allows it in to allow for heating, so it's not as cold. So this is a really cool example. So cooling in warmer climates. This is when the building is, well, it's hot and you want to cool the building, so you're designing it for cooling. So you can elongate the building in the east-west direction. So the shorter sides are the ones exposed to maximum heat gain. So you have shorter area exposed to sunlight. Shade the east and west walls to, once again, reduce the amount of heat gain. Because you've got, this says south-facing windows, but it really means polar-facing windows. It's south-facing only applies in the northern hemisphere because the sun is going around the equator. So the south-facing windows on our side are the north-facing windows on the south side of the equator, if that makes sense. It just means the solar side. So you shade those during, you minimize those south-facing windows, or you shade them during the summer. And light-colored roofs, obviously, because light colors reflect heat, dark colors absorb heat. So that's some strategies you can apply in warmer climates to make buildings cooler. It's not an exhaustive list. This is just kind of the basics. I'll show you, you can get more info if you want it. In colder climates, if you're designing for heating, you would want the south wall to be elongated for maximum heat gain. You want a lot of windows, also allow for maximum heat gain. And if you've got a big building, you can have interior sun spaces if you want to transfer heat to interior rooms. So if you've got, if you've got heat gain along the front, but then you've got a bunch of rooms behind it that aren't getting that heat gain, a sun space is something you can use to alleviate that. So it'll heat the inside of the building, and that will expand. The heat will kind of travel to other parts of the building as well. Thermal mass, usually some sort of earth or masonry or water. It can include concrete, brick, stone, adobe. And in winter, this thermal mass will absorb heat during the day and then release it at night when it's cold. So it's kind of storing that heat for when you need it. In the summer, it absorbs heat from the building other than from outside, cools down the building, and then at night you can use ventilation to flush that heat out. Passive ventilation. Also evaporative cooling towers. These are, you can see them right here. You have water evaporating from the top of the cooling tower, and that creates a downdraft of cool air because cooler air sinks. So as that water cools off, it's going to get denser, it's going to sink, and then you can circulate it to where it's needed. In terms of design, they should be at least twice the height of the space that needs to be cooled. And the higher the tower is, the more cold air is going to be delivered to the building. Solar chimneys are kind of similar, but not quite the same. In this case, you want to maximize the heat gain for those solar chimneys. That's why these are painted black. You want to heat them up as much as possible because the air inside will heat up. And then you can place vents at the bottom of the structure and shade them either with shading structures or with plants. And what will happen is the air in the chimney will get really hot and it'll rise, and then it'll pull cooler air in from underneath, and that results in passive ventilation. So I'm showing you ways of achieving HVAC without needing to put energy into an HVAC system. This doesn't really belong in building design, but it's passive solar and it's cool. This is called a zero pot. What it is, it's 2 terracotta pots with a layer of wet sand in between. And so that sand, 1 is thermal mass, so it acts as insulation. And 2, the terracotta is water permeable. So the pot basically sweats. That water inside the sand travels through the pot when it's hot, and that's evaporative cooling. So they're used for food storage without electricity. And with a good breeze, they can maintain temperatures around 40 degrees Fahrenheit. Most modern day electric refrigerators are between 35 and 38 degrees Fahrenheit. So you can see these are very, very close. And it's a great way of achieving good food storage in hot climates without having to use electricity. And you can apply these principles to anything. So it doesn't have to be food storage. I mean, evaporative cooling works for anything. And then energy modeling. So I showed you a bunch of passive strategies, and you can use computer programs to model those passive solar techniques and renewables. And it will show you much more accurate energy and cost savings with the program. So that one up top, that's a program called HEED that is free. I can show you where to get the software if you're interested. It's pretty cool. It's more basic. It gives you kind of a rough estimate, but it does work. These 2 bottom ones are from a program called IEEE. I took a class on this. It sucks. That program is so annoying. Even our professor who worked with it for years. It's very accurate. It does a lot more than HEED. It's very accurate. This is showing thermal templates. So basically it's saying, if you've got one type of room, maybe there's more heat gain in that room versus another room. So like if you've got a kitchen, you've got heat coming in from the cooking, that kind of a thing. How many people are in the room, that kind of stuff. And so this shows you the different thermal templates that apply to different rooms in a building. And then down there, that is a solar radiation analysis. So it shows you in terms of like,
Sun position?
Well, not sun, well, yes, sun position, but it shows you in terms of if you wanted to put in solar panels, or if you wanted to work on passive solar, which parts of the building are getting the most heat. But yes, this program is an absolute pain in the butt. Even our professor who's worked with it for years, when we were trying to calculate something, he'd be like, okay, this is the part where if you're the praying type, you say a prayer and cross your fingers and hope it calculates and doesn't give you an error. And when it gives you an error, like, all hell breaks loose. There is never a good reason why. It's just stupid. But it is very effective. If this is something you're interested in, this is actually a career. You can become a certified energy analyst and do this for a living. So yeah, cool stuff. Unfortunately, this program on the bottom is very expensive. He was able to get us free access for the 1 semester in the class, but that's it. Otherwise, it's very expensive and they don't have student access to it.
What are the colors for that one?
This one?
Yeah, like what is the dark blue lines versus green neon lines?
So those are different thermal templates. So it's color coded.
So blue is colder?
No, there's just different. So if, like, let's say I'm talking about, like apartments versus kitchens versus hallways, that's just what this is showing.
I see
So,
like hallways.
yeah, so green is hallways, blue, I think it's apartments. Yellow, I want to say might be like supply closets or something, or elevators or stairs.
The bottom row.
The bottom row, I think, has like community rooms, so there's a little bit
Also,
different.
people, I guess.
Yeah, so that's just showing the different thermal templates. One of the things you can do in the program. You can also do like stack ventilation. What else? It'll show like daylighting. One of the things I didn't mention is that you can use passive solar, not just for heating, you can also use it for lighting too. So there are ways to maximize solar lighting rather than having to input energy into electric lighting like we have here. Yeah. Renewable energy. So this is kind of the part that a lot of engineers, I think, associate with sustainable engineering. When I told people about this, the first thing I heard was solar panels. And I'm like, we're gonna spend like 10 minutes on solar panels. There are much more interesting things to talk about. Unfortunately, I don't have all the types of renewable energy I wanted to talk to you about here just because I ran out of time and space in the presentation, but I'm hoping I can still show you guys some cool stuff. First of all, renewable energy, cities or power plants. Anyone have a guess as to which is better versus if you have like a power plants out somewhere versus, energy in a city?
AC is better, right? For moving power across
Where?
AC, isn't AC better for moving power across long distances?
Yes, but in terms of having a plant located outside the city or having energy decentralized, like on rooftops, do you know which is better?
Oh, probably decentralized.
Oh, okay, I was gonna say cities, is another trick question.
Yeah, well, in cities.
Oh, it is?
Well, yeah, like that's you said, like in cities.
Okay, cities as in like have large towers.
As in don't have big power plants. Do you guys know why?
Well, it would reduce, well, you wouldn't need transformers. You wouldn't need gigantic transformers, like step up and step down transformers like you would with traditional power plants. I believe that's one thing.
So yeah, definitely correct. One thing that's also to minimize losses, because the more distance you have to travel from the source of the power to the use, there's gonna be losses associated with that.
Right.
And so having energy produced in the city where it's being used, that's much more efficient. Also reduces the amount of materials you have to use and the cost, therefore, because you don't have to purchase as much of the energy, if that makes sense. So if you're using a solar system, you don't have to purchase as much you don't have to purchase as many solar panels because you don't have as much loss. So economic and efficient. And then there's also the aspect of environmental protections. So if you've got a giant solar farm or wind farm, out somewhere outside the city, that is habitat degradation, and we want to reduce that as much as possible. I briefly mentioned all the things biosphere does for us, right? Air and water quality filtration, pest control, food production, all these things that we want them to keep doing. So the more we can protect natural systems, the better. So there's the environmental reason, and there's also the efficiency, economic, engineering reason. Does that make sense? Energy mix, that's kind of what I mentioned earlier. Is that you want to have a lot of different types of energy being created at the same time, because if something happens to one, you don't want that to be the end of the story. Yeah, you always want to have backups. So if something goes wrong with wind, if there's like wind drought, you want to have solar. If you want something, if you have a lot of clouds and there's no solar, you want to have wind and tidal or geothermal or whatever. Just have multiple ways of producing power. Type of power, AC versus DC, just, different renewables produce different types. So like solar produces DC, wind produces AC, stuff like that. Interesting considerations for the grid. And then you need climate data. So you always want to consider the climate that you're in and the topography and geography of that area. So I'm going to show you, this is really cool. If I'm able to click on this link.
Charge your laptop. Or is it just batteries?
We are good for right now, but I'll plug it in if necessary. So this is the Global Solar Atlas. This was created in conjunction with the World Bank, and it shows basically solar radiation around the world. So let's say you click to the spot in California. you can see it shows the breakdown. So global horizontal radiation, that's what we would use for our calculations. And you can see, optimum tilt, air temperature, all this really neat data that's very helpful if you're doing planning. There's also the global wind atlas. Loading.
Oh, well, how did they get that data? Satellites, obviously.
Probably, I'm actually not sure, but probably that's a good guess. So this is basically the same thing for wind. So if I picked a spot here, wait for it to load, you can see it gives you a lot of this data that you need, so like the wind rows, that shows you the amount of wind and the direction it comes from. What else? Then the mean wind speed at height of 100 meters.
This mean power density.
Where do you see that? Oh, let's see. Power density, I'm not 100% sure. I want to say that that is the average amount of power you could get from a specific amount of wind, but I'm not sure. I would want to double check that. Anyways, cool stuff. And then if you click energy data info right here, wait for it to load again. This is just a variety of different data sets you can use. I haven't explored all these, but they have, once again, created by the World Bank. You can see it at the bottom. And this has cool stuff you can explore. Something else cool I wanted to show you is climate consultants. Can you all see this? Okay. So this was created specifically for California. But you can use it actually for a variety of things around the world. So if you see right here, it tells you can download information from the U.S. Department of Energy, Energy Plus site in the EPW form. And I'll link that later. So if you're interested, you click into it. And basically what that says is the data loaded on here is specifically for California. But if you want other data sets, you can download those from this website. So if I go through this, start a new project, metric, because I hate Imperial, select California climate zone data file. So if I enter our zip code here, that is 91768, do a search, climate zone 9. So basically what this is they've broken down California into these different climate zones according to what the climate conditions are in those zones. So right now we are not in climate zone 6, we're in climate zone 9. I don't know how that changed. Okay, there we go. So open file. And it will show you all of the data for California, or for this particular climate zone in California.
Is the zoning the same thing as what farmers say when they're like, oh, I'm in zone, whatever, farming, or is that different?
I would imagine it's different, but I'm not sure. I know these zones were created specifically for California. I imagine that's probably more in terms of the US.
Yeah.
Yeah, so I'm not sure, but I would say probably not. And then you can go through, sure, California Energy Code, why not? And it will show you these are temperature ranges for this particular climate zone. This is like more temperature ranges, illumination hours that are not given, cloud cover, wind velocity, ground temperature, dry bulb and humidity, and dew points and shading.
I don't know what dry bulb meant in fluids. You know what dry bulb means?
I believe it means not accounting for the humidity, but I could be wrong. I will double check that. So then, okay, so this is cool actually. If you're looking at building design, basically this shows you, it suggests design strategies for this climate zone. What you can do is, like this is, okay, I should back up. Each of these dots there, that represents like an hour of the year. And so you can see right here, you've got 100% comfortable hours. So that means that your building, if you use all these strategies, is going to be within the comfortable temperature range for a human at 100% of the hours. So if I go here, I can see this is number 12, that's at 0%. So that needs to go. 13, that's at 1%, 0.6%, 1.3%. Basically what this just means is I'm getting rid of the technologies that aren't doing much for us. So, because we don't want to spend money on doing those if they're only going to, take up a couple hours of the year. You can see I'm still at 98% here. What else? 7.9, 7.2. So 9.6 maybe. Yeah. Let's see. Play around with these. Yeah, so you can see I am still at 97% comfortable here. 93% comfortable. Okay, that's fine. So basically what that means is that 97% or 93% now of the hours of the year are gonna be comfortable in this building. So go to next. Yeah, whatever. Okay. And what this is it's suggesting strategies for you to use for your building. So let's say window overhangs. I'll give you a description, and then what's really cool is it'll actually link to the 2030 palette. So we talked a little about the 2030 challenge earlier this workshop, and what it is the commitment to get to net zero by 2030 for buildings in California. Well, buildings everywhere, but California committed to it. So this is a cool website. You can explore later. I linked it afterwards, and it shows a lot of different building strategies and materials and stuff that you can use to achieve net zero. And it links to 2030. It links to climate consultants. So if you click on a strategy, you can see more details about it right here. So yeah, cool stuff. And then last, this is the wind wheel. So you can see it gives you the wind speed right here, the number of hours for that wind speed. So you can see on monthly right here, if I click start, it'll actually go through all the months and show you how the wind changes. Yeah. So cool stuff. Really helpful tool. It's not the most accurate. There are more accurate tools out there. But this is just nice for approximating. Let me close that. No. And it's also free. Good free program. The one thing I will say is none of the data sets I showed you account for future conditions, and that's something that's really important if you're talking about climate change, because weather conditions are going to change as we move forward.
How old is the data for that one?
I want to say it's like the last 10 years, but I could be wrong. Let me double check that for you as well, actually. Basically, I know. Okay, so I was looking into this. Apparently, there are data sets that will show you future predictions for temperature and, well, not temperature, climate. But either they are not available at the moment or they are not free. So kind of something you have to, but maybe not something you have to worry about right now, but if you're in a job working for this, that is something you have to account for is, you don't want to design something for current climate conditions if it's built to last for 50 years, because things are obviously going to change. With that, we've talked about where you get your data from, going into the actual energy generation. So this is solar, because everyone likes to talk about solar. The first thing you want to talk about is azimuth. That is kind of the direction it's facing on the globe. So if you've got, let's say, true south, that's facing north. Sorry, true south in the northern hemisphere would be 0 degrees, and true north would be 180 degrees. So like it's your, I think I typed this wrong. I don't know. The point is that if you have a solar panel, 0 degrees is facing towards the equator and 180 degrees is facing toward the pole. If that makes sense. Yeah, okay. You can see that right here, this gamma, that's also the azimuth. It says azimuth, but you can't see it here. There's also the tilt angle, which I believe is the beta here. So if you've got 0 degrees would be, a 0 degree tilt angle would be flat, 90 degree would be vertical, and you want somewhere in between. A rule of thumb is that your tilt angle should be about equal to your latitude. And that's, you'd subtract 15 degrees in summer and add 15 degrees in winter because the position of the sun is changing. One thing is be careful of shading. So if you are working on a building that has solar arrays, they can actually, the solar panels will shade each other based on the time of day. So you never want to put them at an angle where they're going to shade each other. So the optimal angle might not be the best one based on, you know where I'm going with this? Yeah. Then you've got the types of panels, monocrystalline and monocrystalline versus polycrystalline. Monocrystalline basically means that the silicon is formed into bars and cut into paper. So you've got this, the panel is made of like a single crystal. And because because it's a single crystal, there's more room for electrons to flow, so it's more efficient. Polycrystalline cells are made of fragments of silicon that are melted together to form the wafers. And so they're a little bit less efficient, but they're easier to manufacture, so cheaper. That's just one of the things you have to think about when you're looking at solar. Also, solar panels produce DC, not AC. And the grid runs on AC, so you're looking at grid power. You're going to need an inverter, and you also need a charge controller. Charge controller just protects your batteries from like overloads, any reverse charging, reverse polarity detection. Definitely worth it to have one of those.
Which one degrades faster, mono or poly?
I don't know. I would say poly. I think mono lasts longer, but I am not entirely sure.
Probably like 25 years, I think.
Yeah, that sounds about right. Calculations. So peak solar hours are how much solar radiance the location receives over a period of time. You always want to use your global horizontal irradiance to calculate peak sun hours. People use direct normal, that's wrong. Use global horizontal. You can see that's what both of these maps here are in. This one's from NREL, which is the National Renewable Energy Laboratory. It's a great resource if you are interested in renewable energy. 1 peak sun hour is about equal to 1 kilowatt hour per square meter of solar energy. And LA has approximately 5.44 average daily peak sun hours. Assuming a tilt of 0 degrees, the horizontal panel, and an azimuth of 180 south facing. And if I didn't mention this before, you always want your azimuth to be facing the equator. So it would always be ideally 180 degrees in the northern hemisphere. If you wanted to calculate your estimated solar output, that would be your peak solar hours times the wattage that your panel is rated for. So if you've got, let's say, a standard 400 watt panel, you multiply that in LA by 5.44 solar hours per day, and that would give you your watt hours for 1 day. You can also calculate your peak sun hours with NREL's PV watts calculator. That's once again National Renewable Energy Laboratory, great tool. This also accounts for stuff like cloud cover and pollutants in the air. So whatever your peak solar hours should be, they might not always be because of accounting for those environmental conditions, but this calculator takes into account those other factors. So it's a great tool. Transparent solar, this is a new one. That's kind of cool. Stands for, TLSC, that's what it's called, stands for Transparent Luminescent Solar Concentrator Technology. And these are made from, well, they're made from glass, but they have coatings on them that are made for organic salts that glow as another invisible wavelength. So what happens is those salts selectively harness UV and near infrared wavelengths that are outside of our visible spectrum. And they guide those wavelengths to the edge of the plastic window, plastic, I'm sorry, where thin PV solar strips will convert it into electricity. So you can see what's going on right there. It's selectively harnessing the infrared and ultraviolet and letting the visible pass through, so we can still see through it, which is cool. And that up there, the cars, that is actually one of the first places this was implemented, the office building of one of the companies that invented these. So you can see they're actually like transparent. They're about 10% efficient right now. So regular solar panels are about 17 to 20% efficient. So not quite as good, but they're more widely able to be implemented. So, if you imagine all the glass we have around, all the different buildings in our world, a lot of capacity. And the articles that I saw about this were even talking about using it on stuff like cell phone glass or laptop glass, car windows. So really cool ways of harvesting energy from, various different sources.
This one would be like a hybrid book.
Yeah. So the coatings are made from light absorbing dyes. Unfortunately, they will not tell you which ones, but supposedly they're non-toxic and earth abundant minerals. Interesting applications for passive solar. So in terms of, we talked about passive solar earlier, right? Normally windows are where you have the most solar heating, but if these are absorbing your infrared radiation, that's gonna be very different. So interesting concept. Horizontal axis wind turbines. So we're getting into wind. I don't like these. They're big, they're loud, they're expensive, they're just big and difficult to maintain. They take up a lot of land, which we talked about is bad in terms of habitat preservation. They also have to yaw or rotate to face the wind, so that's annoying. And they're really bad in terms of groups, because what happens is that downstream turbines will experience turbulence from upstream turbines. So when you have large groups of them, having turbines together will actually decrease their efficiency, which sucks. If you were interested in calculating the power you get from these, that's the equation up top here. So power from a turbine is the is that the power coefficient? Double check what that's called. Hang on. It is the power coefficient. Forgot I couldn't see my notes when I was translating. It's the power coefficient. Multiplied by the cross-sectional area, that would be like this kind of area here, times the density of air, and then the cube of the average wind velocity. And that would be your average annual power for wind turbine. So like I said, I don't like these. I like these better. These are omnidirectional or sometimes called vertical axis wind turbines. No, that's no. Okay. You can see, you can't really see because the picture is here, but this isn't a vertical axis wind turbine. And what happens is that the wind just kind of spins it around the vertical axis. So it's not having that issue of having to face toward the wind, it's always facing towards the wind. This one here in particular, I believe the model is called the ice wind. And you can see it's got those little blades in the center. Those are for slower moving winds. And then you've got the blades on the outside for faster moving winds. So it can capture wind speeds from different wind velocities, so that makes sense. You've also got, people talk about rooftop solar a lot. This is actually rooftop wind, this down here. So that's another type of vertical axis wind power technology. It's really cool. These I really like. This is a type of what's it called? It's an enclosed wind turbine, if that makes sense. So enclosed wind turbines they're safer, they're more efficient, and make use of the wind funnel effect. So if you see this equation up here, this is basic fluid mechanics. The flow rate is the area, cross-sectional area times the velocity. So you reduce the cross-sectional area, you increase the velocity, basic principle of fluid mechanics. So that's really cool in terms of wind power, because if you reduce the cross-section, you can get more power. And that's what this does, is the blades are inside and they turn inside. And you got this coating outside that funnels the wind into those blades. So much more efficient and just safer. I like these ones. Yeah, that was one of the other issues with big solar, big wind turbines, is that they're bad for wildlife. So these are just so much safer. Also, we mentioned the wake effect in that last slide, that they're not good for large groups because of the turbulence. So vertical axis wind turbines aren't as efficient as horizontal axis, but that's on their own. When they're working together in a wind farm, vertical axis are much more efficient because they don't have that turbulence issue quite as much. And so they're able to be grouped closer together. That saves space. And once again, efficiency. Also, they have gearboxes and generators at ground level. So maintaining them isn't as hard or as dangerous, I guess. You also don't need the space to turn towards the wind. We talked about that. Excuse me. And you also don't have gravity-induced stress and strain cycles on the blades because they're not hanging off of a giant structure.
You know what the efficiency for the omnidirectional one is compared to the regular wind?
Unfortunately, I don't. I wish I did. I know, huh?
At least these are more sustainable, so on the long run.
Yeah, I know they're less efficient when it comes to a specific singular turbine, but more efficient in groups. This one right here, I love. This is called the O-Winds. This was actually developed, I think, in Europe to take advantage of renewable energy tax credits for people who lived in apartments and couldn't do rooftop solar. So they're like, I want to say they're like that big. And what these are, we call vertical axis wind turbines omnidirectional, but these are the ones that are really omnidirectional because you can input wind into them from all directions, including vertically. And basically what happens is that this ball, which I believe is 3D printed, it just spins around the axis, and that's what creates the generation. So there's actually no blades in this one. And these are great for cities where the winds are a little bit more chaotic, which is what they were developed for. They also look cool. Like these are like lanterns. They look like lanterns.
Some lights on it.
Exactly, right? So that's one of the things that you also need to consider with renewable energy in cities is how does it look? Because you don't want to be an eyesore. Which brings us to our next slide. Does anyone recognize this? I'm just curious.
No.
No?
No.
How about now?
Oh,
Okay, I love this movie. This was a scene from Akira 6. And these are airborne wind turbines. This is actually the first place that I learned about them. Was in this movie. Which I love. So airborne wind is cool because it can take advantage of winds at higher altitudes, which are faster, more persistent, and less turbulent. Also, a lot of these two styles of these devices can move across the wind, which harvest more energy. So they're able to get more energy than stationary wind turbines on the ground. Easier to maintain and service. And a lot of times they use less material, so cheaper because they don't have the giant tower. So there's three types. You can see what here is the blimp style. This is basically just regular vertical axis, or basically a horizontal axis wind turbine, but floating. And then up here, this is a glider style. It's actually a type of UAV, which is really cool. What happens is that the propellers that you see on the front there, those will turn as it's trying to get into the atmosphere. What do you call that? Into its state of flying.
Yeah.
Like on the word here. Lift off. There you go. And once it starts flying and it gets into that self-sustained lift, those propellers will actually start going backwards and turn into generators. And so then this will go in a circle, and yeah, and it's connected to that tether there that relays electricity back to the ground. Then you've got kite style. I love these. So you can see that kite right there and this pattern that it takes. So what happens is it flies in this figure 8 pattern. And as it does that, it's connected to a generator on the ground. So it pulls the generator and turns it as it's flying in a power stroke. And then it kind of gets pulled back and then it pulls it again and creates power that way. There's a company that was using 2 of these kites at the same time. So that when one was in power stroke, the other was in the coming back stroke. Yeah, really cool. Oh, something I forgot to mention earlier. Wind funnel effect. Really important. One of the things that has the potential to happen with climate change is that winds are driven by temperature gradients, right? And so one of the things that scientists are predicting could happen with climate change is that the poles are going to get warmer. And so there's going to be less of a temperature gradient between the areas of the earth, and that's going to affect the wind patterns. And it can create these things called wind droughts. So not necessarily a guarantee, but likely to happen at some point in the future. Talk about the fact that this already kind of happened in Europe. And so the ability to increase wind speeds through this wind funnel effect is really important to maintain the efficiency of wind power. So that's one of the other reasons that I really like these. Should have mentioned that before. Okay, urban wind, hydroelectric, kind of repeating pattern. Anything that's like the normal, I don't like. Old school, yeah, but also just bad. These are about 90% efficient, and that's kind of the only thing they have going for them. They do produce a lot of power. They are relatively cheap to operate after you get over that initial cost. But they're really, really bad for your environment. Actually, may have pissed off a couple people telling them this. So what happens when you create these reservoirs, one, you're flooding a large area of, whatever it was before. Natural habitat could have been areas people lived. So governments usually have to pay relocation costs, people who live there. Large scale flooding, relocation, and destruction of ecosystems. And then you've also got the effects of the water quality. So when you flood an area like that, you get, normally you have, like a little bit of river water, and there's usually vegetation coming out on both sides. So it's relatively cold and it's fast moving. So it doesn't have a lot of time for heat, a lot of time to be heated by the sun. When you make a reservoir, that all changes. So not only do you not have shading, you also have a large expanse of water that is exposed to sunlight and is not moving very fast at all. So the top layers get heated, and then because it's much deeper than the river, the bottom layers get colder. And what happens is those colder, stagnant, and for nature pollution, dams, what happened is they changed the hydrogeology of the site. I think that's the right word. And so you get a lot of sediment buildup behind the dam. Sediments contain nutrients. So you've got nutrient pollution in that reservoir. You've got colder and more stagnant waters, and that results in lower dissolved oxygen in the bottom. In the top, you get warmer waters that are also very slow and have nutrient pollution, and that results in algae growth. Cyanobacteria in particular can release toxins when it grows, and so that's not great. That was an issue with the Klamath Dam, I believe, in Northern California. There was a series where that was an issue. Basically, just really bad. I don't know why these are. I don't know why people think these are a good idea, because they're not. They're never a good idea. So you've got algae growth there that can release toxins into water. You've got that, dissolved oxygen pour water flowing downstream, as well as nutrient pour, because the sediments all get blocked behind that dam. So that has really detrimental impacts on the ecology further downstream. Plants and animals that live there don't have enough dissolved oxygen, so they basically can't breathe. And there's not enough nutrients for plants to grow, so just bad. Yeah.
So I do gotta head out.
So what?
How do I get access? Like, is this gonna be posted anywhere? Like,
Yes. This will be posted on our Discord and on Discord. It'll definitely be posted on our website later today, or later this week.
on the website?
Yes.
Okay.
So the rest of the recording will be posted there, as well as the PowerPoint.
Okay, cool.
Yeah.
Thank you.
Yeah, no problem. Thanks for coming. So getting back to this, it also prevents fish from reaching their breeding grounds when you have those dams there. There are fishways that will supposedly help with this. There's debates for whether they actually work. A lot of times they don't. And there's also the issue when you have multiple dams along a river, that just decreases the chances that those fish are ever going to get back to their breeding grounds. I know you're gonna wonder why that's important, because that's our food supply. Like, that's literally our food.
Dams work, so like, do the fish co-line with the water? Do they just shoot through?
That's definitely an issue. That is definitely an issue, that fish will get hurt in the turbine blades. I believe the fishways are only supposed to get them upstream. Downstream, yeah, I've been a little unclear on that myself, because I don't understand why they're going through turbine blades. That just seems like bad design. Yeah, basically just bad. And also there's a lot of effects on the ecology of the system upstream, because when those migratory fish die, their bodies fertilize like the entire area. So like salmon, for example, yeah, I'm sure you know this, yeah? Yeah. So the nutrients from the salmon impacts the health of the forest, and that forest, has implications for the water cycle and just all kinds of stuff. So the less impact you have on it, the better. Also, methyl mercury. When you flood an area, a lot of times the soil will contain tiny bits of elemental mercury, which isn't a problem in elemental form. But aquatic environments contain aquatic bacteria that will convert mercury into methyl mercury. Methyl mercury is an organic form of mercury, a much more bioavailable form. And so that basically makes it much more toxic. It's much more able to bind to living cells. And so that's, a problem. Sure, we have renewable energy, but then you're like having toxic water and getting rid of our food supply. I have issues with these, in case you can't tell. If you were interested in them though, that is the formula for power generation up there. So the density of the water times gravity, of course, then the head, which in this case is really just the height difference, multiplied by the volumetric flow rate and the efficiency of the turbine. And then you divide by 1,000 to get kilowatts. Divide by 1,000 to get kilowatts instead of watts. Run of the river hydroelectric is a little bit better.
Still Still not good though.
No, they're okay. Basically with this, they're just don't produce as much electricity. So basically what these are is that they're built to generate electricity with the flow of the river instead of having a dam that controls the water flow. So there's little or no water storage, which makes them less reliable than traditional hydroelectric. But they're cheaper and they're less environmentally damaging. So these are better options who just don't produce as much power as large scale hydroelectric. And the battery's running low. Give me a sec while I plug my cable in. So these are a technology that are not really established, but kind of coming out that I think are really cool. And basically this is a vortex water turbine. So what happens is you see the water in and water out. And so the water it's just briefly diverted from the river. It runs through this turbine. And then it goes back out and flows back to the river. So very minimal impacts on the river system and its hydrogeology and ecology. And that is two different. Okay. The potential energy here is converted to the traceable kinetic energy in the center of the vortex, which utilizes a vertical axis turbine to produce electricity. Give me a sec to plug this in. Just check it's actually charging. Good. Okay. There's usually a screen over the inlet here that prevents wildlife and trash from entering the system. Extremely low head, usually like 0.7 to 2 meters. So not very compact, doesn't take up a lot of space, very high energy efficiency. These can produce from less than 500 watts to 100 kilowatts. So once again, lots of power. Not as much as a large scale dam, but good for local power generation. You can also aerate, the turbine also aerates the water as it goes to the turbine, so it's beneficial to water quality rather than detrimental to it. And once again, minimal environmental damage. So I like these, I think they're cool. But really not for large scale use. And I just test the escape screen. Oh, piezoelectricity, this is cool. So if you're not familiar with the piezoelectric effect, this is kind of electrical thing in which the deformation of certain materials will generate an electric current. Make sure to check where I'm on time. I do not have much time at all. Okay. So what happens is this is a quartz crystal. Quartz is like the most common piezoelectric material. There are other synthetics materials, but this is what it looks like when there's no stress. When it's compressed or tensed, when it's in tensile or compressive stress, what happens is the alignment of that hexagonal structure changes. And so you can see here, you've got 1 negative and 2 negatives versus 2 positives and 1 positive. So that charge gets thrown off. And so you can see this side has a net positive charge and this side has a net negative charge. And the same thing here reversed. And so that creates a electric current. And so when these are, in stress or in tension or compression, they create that electric current, and you can use that to power devices. So you produce AC power with this. You do need a bridge rectifier to get DC current. So that's what's showing here is this AC. I don't really want to go into the details of how these work, but basically it's a series of diodes because diodes only let current flow one way. And the way they're arranged turns that AC into a DC current. And right here, you can see that's a piezoelectric transducer. So that's kind of the thing you would work with if you wanted to experiment with these.
You put it in tension compression though, because you're gonna put work into compressing it and stuff.
In terms of one of these things, you hit the disc.
This?
Like that white circle on it, that's the quartz.
Yeah.
You hit the quartz.
Okay, so someone will have to put in the work and like hit it.
Yes. So it's kinetic energy work.
Okay.
Yeah. Can't remember what I was gonna say next. But this is like from energy harvesting, and it's really good design for small electronics because you're increasing the battery life. So if you've got, a consumer, if you're making consumer electronics, just a good way to increase battery life. Like you're making your customers happy. And you're reducing the electricity needs from the grid. So just cool. So these are really cool examples of energy harvesting. Yeah, energy harvesting basically just means, figuring out where the waste energy is in the surroundings and taking advantage of it. So this right here, that's a piezoelectric dance floor. Some brilliant dance club in I think it was, I want to say Holland, Netherlands. They realized that people jumping up and down their dance floor were generating electricity, and they can use that power the club. So you can see how it works right here. The crystal blocks are squished by the springs. And that squishing, the compressive stress produces electricity. So that's cool. These right here, this is also kind of research going on right now. That is a shock absorber. And the shock absorption from the car is being used to generate electricity. So you can use that those waste vibrations and waste energy to recover some electricity that you were using in the first place. So I love this. I think it's super cool. I love these too. What these are wind turbines based on like cars, because you don't actually need wind to generate electricity from wind turbines. You just need moving air. And so these are taking advantage of the fact that there are cars moving past them and generating air, like moving air. And that's, I think, is super cool. So this is a concept right now in energy harvesting that I think is super cool. Okay, next section, excuse me, is batteries. So I think we're all familiar with lithium ion, right? That's kind of the big thing right now. Lithium ion are good, but lithium is getting more and more scarce. So finding an alternative is definitely a priority. Lithium batteries are also explosive and can catch on fire, and they're hard to recycle. So sodium ion batteries, which are kind of what the technology that's being developed to replace them. You heard of these yet?
Car is using the sodium.
Oh, interesting. Okay. So these are definitely safer than lithium ion. Lithium is temperature sensitive, sodium is not. So sodium is non-flammable and non-explosive. They're much safer batteries to work with. And because they're not temperature sensitive, they don't experience heat runoff. That's the phenomenon by which the heating of the lithium battery decreases its capacity over time. And that means that sodium batteries have more charging cycles, so extended lifetimes. So not only, sodium is also the sixth most abundant element on Earth, 1,000 times more abundant than lithium. And rather than mined, they can be easily harvested from ocean water. So not only are these like just better technology not only are these sustainable because they're more easy to produce, they're also just better technology because they have more charging cycles and they're safer. They are currently less dense than lithium because sodium as an element is heavier, and so it's the same charge with more weight, therefore reducing the energy density. But they are catching up. I don't know exactly how they're doing it. They are making advances that are getting sodium batteries closer and closer to the capacity of lithium. They're also one of two battery technologies that could meet the energy efficiency targets of greater than 90% for stationary battery systems by 2030. I think one company has already achieved an efficiency of 92%, which is way better than lead acid. These are actually have much greater capacity than lead acid already, so they're really just competing with lithium at this point. And they're cheaper because lithium, as well as other materials like cobalt that are necessary for lithium batteries, are getting more and more expensive. So these are just better technologies. Yes, and unfortunately they don't come in like small sizes right now, I think because they're just starting. So you can see these were just recently implemented in Australia. But I expect small sodium batteries coming soon, hopefully. Lithium batteries, these are cool. So lithium ion batteries usually use some form of carbon as the anode, usually graphite. And synthetic graphite production, the raw materials are generally petroleum coke or coal tar pitch, so fossil fuels. And the process of creating synthetic graphite involves heating the carbon to temperatures of 3,000 degrees I didn't put units. I assume Celsius, so I gotta check that. For 4 weeks at a time, and the energy often comes from coal-fired power plants. It's not great. So what this paper company actually did is they discovered that they could take the waste lignin that is extracted from paper pulp when they make paper, and they can use it to make a replacement carbon material for battery anodes. So it still has to be heated, but not to temperatures nearly as high as for graphite. And the resulting structure is actually more amorphous, so it allows higher mobility of ions and shortens the herding times. So these are available. I move this. That's actually battery right there. So these exist. Sand batteries. So we've talked about electrical batteries in past 2 slides, but not all energy storage has to be electrical. So you can have thermal storage, and that's what these are. Sand batteries can store heat at 500 degrees to 600 degrees for a couple months. Basically, you charge them with renewables. There's heating elements inside, and then they store that energy. And when you want it, you distribute it in the form of hot air. So there's like heat exchange pipes, and you would just heat those pipes with the hot sand, and that would get distributed to people who need it. Sand is very expensive, very inexpensive. It's durable, and it's readily available. So these are really cool. This company is one of the first who does it. They provide heat energy to their entire town, and I believe they work on like 2-week charging cycles. So yeah. Huh?
Heating buildings?
Yes. So they use the hot sand to heat air, which then is piped to buildings. Pump storage hydroelectricity. What this is using gravitational potential energy to store electrical energy. So when you have excess energy available from like renewables, you would use energy to pump water or maybe another fluid, usually water, from a lower reservoir to a higher one. And then the water passes through turbines to generate electricity. You could use a higher density liquid if you wanted to reduce the head, so you wouldn't need as much storage capacity or as much fluid, because you have more energy coming from that one little bit. Unfortunately, it doesn't scale well. You have to find suitable sites for it. Efficiency is only around 80%. And you have to find like this here is kind of special. It's a very specific, reservoir on top, the reservoir on the bottom, kind of hard to find that. Once again, not scalable. And then you can see I've got formulas right here. So this is for energy and then power. And power is really the same as for hydroelectric. It's the same thing. Liquid weight storage is kind of the same concept. You're using gravitational potential energy to store, to store what was originally electrical energy. But you use that extra energy to lift weights in a flying system. And when that energy is needed, the mass is lowered and the pollution generator. And this is just, mass gravity, change in height. I think we're all pretty familiar with that. Flywheel energy storage systems, these are cool. So it stores the kinetic energy in a rotating mass, and that mass is connected to a motor generator. And so you have a rotating motor, right? And that basically starts this mass here rotating, and it keeps rotating. And this is a way to kind of account for like gaps in energy generation to the grid. So as soon as the generator stops turning it, it can turn the generator. It can go to from full discharge to full charge in a few seconds or less. They generate AC power, can be installed anywhere, so you get very little space, and they can be cycled very frequently with little wear, so high durability. Oh, forgot I have the next slide. Here's the formulas. The faster the rotational speed, the more energy it can store, and you can see in the formula here. So energy is 1/2 times what is that? I'm blanking on it. Moment of inertia. Half the moment of inertia times the angular velocity. Nope, we're not sharing. We're going back to the slideshow. Nope. And then you can see here you've got max power output and maximum tensile strength, which depends on the material. So lighter materials, once again, to achieve higher rotational speeds, which means conserve more energy, but those materials need high tensile strength to withstand the high centrifugal forces that it's under. To increase the efficiency of these systems, They use ball bearings or magnetically levitated bearings to reduce friction, and they're operated in a vacuum to reduce drag. So they can be very highly efficient. Once again, just a bunch of ways of storing energy in non-traditional systems. So we don't need batteries or electrical batteries to store energy. You can store them in a variety of forms. How much time do I have left? 10 minutes. Okay. Water quality. So my plan today was kind of to have a variety of different sections that would hopefully be interesting to a variety of different types of engineers. This is more of our civil section, because civil engineers work with water. And I want to talk about water quality, the way that ways to filter water that isn't necessarily what you have been taught in school. So the first thing is with plants. If you've heard of hyperaccumulators, these are different plants that can accumulate toxic heavy metals in their tissues. So you've got wild sunflowers there and water hyacinths up top. Those are two really good hyperaccumulators. What happens when they are contaminated is you burn them and the toxic waste is stored, and you can also extract metals from that ash. So that's kind of a cool concept in terms of something I discovered like yesterday. It's called biomining with phytoextraction. So you can actually mine metals using plants. I thought was cool. Then you've also got nutrient filtration through constructed wetlands. So nitrates and phosphates, that's a lot of nutrient contamination comes in that form from like artificial fertilizers and stuff, as well as suspended solids. So this kind of a marsh setting is really good at filtering out those extra nutrients. Plants also release dissolved oxygen into the water during photosynthesis. So great for enhancing the water quality in that way. And Arcata Marsh is the case study I wanted to tell you about. That's actually the picture is right here. Arcata Marsh is part of the water quality treatment system in the city of Arcata in California. And they use this marsh as part of their water quality treatment system. So yeah, I just think this is cool. Like, why would you have a disgusting water quality treatment plant where you can have this beautiful marsh that provides, habitat for a variety of species, and is great for people because they like hiking there and bird watching? Just better. Why would you not have this? Like, why not? Though while we were on plants, the one thing I did want to talk to you about is bioremediation. So this is something that I think engineers should be aware of in case of accidents. Like, I think we talked about that toxic chemical spill in Ohio earlier today, as well as the variety of things that can go wrong in industrial settings, for manufacturing or working in a plant. So plants are a great way to bioremediate areas. Normally, the protocol for dealing with hazardous waste like that when there's a spill is that you just take the contaminated soil and you dump it somewhere, and it's usually somewhere with less regulations, so you're not actually fixing the problem, you're just dumping it on a different community. Yeah, not great, not a nice thing to do. And then you take clean soil from like perfectly good habitat that you shouldn't be messing with and put it in your mess, clean up your mess. Or
like dogs.
Yeah. Exactly. So not a great solution. And it's also really expensive. This is way cheaper. It does take multiple growing seasons. But in comparison to waiting for the funds to clean up the normal way, it's really not that much of a difference, because like the other way is really expensive, so you're never gonna have the funds. Yeah, that's like why we have so many toxic sites just sitting, not doing anything, because no one has the money to clean them up. And like what happened in Ohio, right? The EPA told the company they have to clean this up. So I think this is a strategy that engineers should be aware of in case something like that ever happens at a company they work at. Talk about little plants. Mushrooms also are great for breaking down organic pollutants like oil. I believe there were a couple case studies where oyster mushrooms were used to remediate oil spills. Worked really well, actually. I think they got like 97% remediated. Pretty cool. So yes, I wanted to explain that while we're talking about plants, just how to clean up toxic spills if that ever becomes an issue where you're working. Bivalves. So looking at water filtration, oysters, mussels, and clams, they will filter out algae, phytoplankton, nutrients, bacteria, and organic matter. Because that's the eight filter feeders. One adult oyster can actually filter in 50 gallons of water in one day. So you've got a bunch of them. It's great. Also, if you have oysters and mussels and clams like this, it will simultaneously provide habitat and shelter coastal cities from storms. This actually relates to a case study, a project going on right now in New York called Living Breakwaters. I forget which hurricane it was, but after one of the more recent hurricanes, they were trying to figure out how to make the city more resilient against future hurricanes. And this was a proposal that won. And basically what we're doing is they are building oyster reefs off the coast of the city. One, to protect the city from future natural disasters, because barrier islands, reefs, stuff like that, mangrove forests, those are all natural features that will shelter cities from storms. They absorb the energy before it gets to them. And so that's one of the functions. The other one is to clean up the Bay Area. So this is just something I thought was cool to mention if we're talking about water quality. Biochar. This is a charcoal material that's produced through pyrolysis. It can be made through agricultural waste, including wood chips and nutshells. So once again, utilizing waste materials. Very, very high specific surface area. It can be greater than 400 meters for 1 square gram. 400 square meters per gram. Square grams are not the thing. These can absorb bacteria, heavy metals, nutrients, pHs, and other contaminants. We are actually looking into this. We were looking into this for a project I was in for a class, looking at cleaning up E. coli. And there were studies saying that this could absorb E. coli really, really well. There's all kinds of stuff that it can do. However, it can be clogged with organic matter, so other filters like sand and gravel should be used beforehand. Also really cheap and expensive. So if you're looking for cheap ways to filter water, this is a great thing to do. Actually, I was at the career fair a couple weeks ago and ended up talking to a bunch of water people about this, and they all knew what it was and like used it in their products. This is definitely something you're going to use in the field if you ever go into water quality. I also mentioned plants too, and they were talking about water quality filtering of plants. So, like this is all stuff that is used in the field. Flow forms. This is cool. I learned about these in permaculture design. And basically what it means is you're using the geometry of the shape to increase the dissolved oxygen content of water. They're an alternative to aeration turbines. So they're a way to do it passively without inputting energy into the system. So the shape of these makes the water swish back and forth. And because of that, it's picking up air and picking up oxygen from the air. So if you've got water that's flowing downhill, this is a great way to aerate it without using aeration turbines. If you ever go to a website that's selling these, they will say like the weirdest stuff about like stuff that just doesn't sound scientific. It's so weird. And I'm like, what?
They'll like use lingo like aeration rate or something.
No, they'll just like talk about how like the water increases the structure increases the life-giving force of the water. And I'm like, what? Anyways, but it does increase the dissolved oxygen, which is really what I'm talking about it for. And you can see this chart right here. Dissolved oxygen. And so 9 out of 10 ppm is like ideal. And there was a site selling these that was saying it could get up to like 9 ppm. So they do work. I don't know what these sites are talking about, but they work for aerating water. That's all I care about. You can also use fountains for similar effects. I was looking at one of the posters in the civil engineering department. They're talking about they were working on a park design and they used fountains for the same thing, except this is just a way of doing it passively. Once again, energy efficiency. Yeah. How much time do I have left? 2 minutes. Okay, and we started late, so I'm like right on time. The last thing I want to talk to you guys about is carbon capture. Because you have to, once again, right, we talked about emissions and dealing with emissions and the taxes that could possibly go with emissions. So if you're working in steel manufacturing, for example, you can, if you don't capture those emissions using some sort of carbon capture, that is you're going to get taxed for that. If you are, like, let's say if you're working with the EU, right? That's what we talked about earlier, that it just passed a border tax for this. So for manufacturing, it's taxed. And in the future, if we do see economies start relying on this kind of carbon taxation system, if you're working on product design and you're buying from a manufacturer, right? That's going to be part of your embodied carbon. So your taxes could kind of get passed, or their carbon,
Is your carbon.
yeah, like their embodied carbon is going to be part of your product's embodied energy. And so if you are not careful about that, that's a way that you could really like screw yourself in terms of taxes. If we start seeing that, and I kind of think we will eventually, something to be aware of. Also a good way to reduce what's it called? Making on the term here. Historical emissions, for lack of a better, making on the actual term here. Way of reducing historical emissions and capturing unavoidable emissions. So there are some emissions that will be unavoidable just because that's, you know, like steel making, for example, or cement, right? As much as we try, it's just not gonna happen. So this is something you can work on to kind of prevent those from, you know, if they're created, you can prevent them from at least getting into the atmosphere. So direct air capture, what happens is that the fans draw the air into collectors and through specialized filters that capture the carbon dioxide. And once the filter is saturated with carbon dioxide, the collector is closed and heated, and then it releases it. And then you can take that released carbon dioxide and do something with it. So you can either like sell it to greenhouses or for industrial processes, or you can store it in the ground, which I don't want to talk about next. There are a couple ways. This is where it's like drawing air capture, drawing carbon dioxide directly from the atmosphere. That's kind of a way to make up for legacy emissions, which is the word I was missing earlier. There are also ways you can do it where you are capturing specifically from a source. So let's say like a factory, you would have, you know, like the filter would be directly above the source emissions. You'd be capturing it as you produce it. Yes. So this is carbon storage. So this is a company called Carbfix that created some cool stuff. They're based in Iceland. And what they do is they capture the concentrated carbon dioxide and they mix it with water and they pump it underground. And the carbon dioxide in the water will react with the underground rock and turn to stone. So they use young basaltic rocks that are in Iceland. They're fractured, they're porous, you receive salts. That's kind of how it looks, and it's highly reactive. So the mineralized carbon dioxide will form carbonate minerals, including calcite, and that just kind of appears as white flecks in the basalts. At least 95% of the injected carbon dioxide mineralizes within 2 years, and it's possible to store over 100 kilograms of carbon dioxide in every cubic meter of basalt. So we have plenty of carbon storage capacity all over the world. There have been experiments in different types of rock, a lot of research going on in this field. So if you don't want to sell your carbon dioxide for industrial processes or greenhouses or stuff like that, this is what you do with it. I think that is pretty much it. Oh, resources. So I linked some cool stuff if you ever want to look into these. A lot of these we saw earlier, but strictly design guidelines, that's where I pulled a lot of the product design stuff to talk about from earlier. Climate consultants, there's the link to download it. There's the weather data that it comes from, 2030 palette, and just a lot of other stuff. Product drawdown, you should definitely check that out if you want. Yeah, cool stuff. If you want to check it out later, it's here for you guys, and this will be linked on our website again. So yeah, does anyone have questions? No, okay, I think we've got our questions as you went through. Cool. All right. Thank you guys for coming. Cool. Stop sharing.